Hi, so my name is Justin Kenny. I'm a member of sdmay24 microcart team. I'm here today to record this video to kind of give a summary of our overall team's work on the microcart project and some of the next step for the next team to pick up after we're done. So for the microcart project, generally has two sort of focuses. The first one is MP4, which is a lab given to 488 students. Microcart is generally responsible with maintaining that lab and making improvements to it to make it a better experience for next year's 488 class. The other is the FlyPi, which we'll get into more details later, but it is a large quadcopter drone that can be used by researchers to test some more advanced control system algorithms. Before watching this video, I would recommend that you watch last year's GroundStation video to understand kind of where we came from, what we started with, and so that kind of can help you understand some of our decision making on the project. Before this video, I would absolutely recommend that you read the MP4 lab document to get some better understanding of the concepts, and definitely also the bootcamp document so that you know kind of what's ahead. So another note related to the Git repository, with each slide that I have in this slideshow, I have in square brackets where applicable the appropriate folder in the microcart repository where you can find that component that's mentioned in that slide. So at a high-level overview, it's easiest to think of the microcart infrastructure in three distinct parts. First one is the front end or user interface. The next one is the back end and adapter. And then the last is the drones or other bots. So the back end is generally the central nexus. It connects all the peripherals and handles all the incoming and outgoing packets. That's the one in the blue here. It sees and knows all information passed between every other component. And the front end is what the user uses to control the drone. It's either, as of right now, a GUI, which is written in C++, or a command line interface that's written in C. And the users can use either of those to view logging data, send set points, change parameters. I guess except for in the case of the command line interface, you can't visualize the logging data. And so this red part down here, the Crazy Fly adapter, that was written by our team. That is a Python application that translates packets from the back end into CFlib function calls. And CFlib is a Python library created by the manufacturer of the Crazy Fly BitCraze. And CFlib sends packets directly to drones. So packets come from the back end. CFlib adapter translates them into drone packets, essentially. So the GUI, that's in the GroundStation GUI folder. It's written in C++. This is the current. I have a picture here of the current one used for the MP4 infrastructure. It has some known issues, crashing. Sometimes the logging can be unsteady. Currently, the logging is handled by a file. So a path is sent back from the adapter, and then the GUI opens that file and then reads points from it. We think this may have some slowdown, maybe causing some slowdown issues, but that'll come in a future slide. Another big issue is dropped set points. The drone firmware seems to time out after about 50 milliseconds. We can't really figure out how to change this on the firmware side. And so thus far, we've been having our adapters and GUIs send messages every 20 milliseconds to keep the set point updated, because otherwise the drone will set it back to zero if it doesn't receive another set point. And this can cause some issues, especially when you have all systems running at once, since the slowdown that is caused by running all of the threads can sometimes cause some set points to not be sent. And so we started digging into this, but we were never able to find a conclusive answer as to why this is the case. But there are going to be other videos, YouTube videos on the YouTube channel with more details on how to play around with the GUI in Qt, and some other issues or other information about it will be in those YouTube videos and on the wiki on the repository. So the next component is the backend, which is in C. It's very critical to look through and understand before you start MP4, since it's kind of the central nexus, like I said before, and it handles communications from cameras, from test stands, any other peripherals. All of that is wired through the backend. But for its most basic use, MP4 purposes, it essentially forwards the packets from the GUI to the Crazy Fly adapter. Now, it has way more capabilities than that, but for the most baseline MP4, that's its essential purpose. So the Crazy Fly adapter, which is written in Python, was written by our team. And if you watch the previous videos, like I recommended of last year's team, you'll see that they did not have this component. They had two separate components, CrazyFly adapter and CrazyFly GroundStation. Now, the reason we updated this to be this iteration of the software, as recommended by last year's team, is that two main reasons. The extra hop in between those two components could cause a lot of performance issues, and sometimes the GUI would freeze without warning, and it would be very difficult to recover it. And second, the old CrazyFly GroundStation was written in C++. It was very hard to read as a code base. We hope that ours is a lot more understandable, and it uses the open source CFlib library provided by BigCraze, so a little better integration with the drone from more modern software. So there are three important classes in this setup. First is the GroundStation socket, which contains functions to encode incoming packets and decode outgoing packets. This main class in the middle has two queues. One processes input, one processes output. CrazyFly connection takes the incoming packet, figures out which CFlib function to call, and does that. And then any log data is handled by the log file handler, which places the data into files. Now, for the FlyPi is this large quadcopter here you can see in the picture. A couple of notes about that. It's useful for quadcopter FlyPi development to get a Raspberry Pi 3 from ETG. You can lend them. That's helpful mostly because it has a larger board to work with, and the tutorials found online work a lot better on the Raspberry Pi 3 than they do on the 02. They don't require as much modifications to get them to work. Or even better yet is you can order a Raspberry Pi 4 for development, since it has a second UART, which is very helpful for debugging. And the tutorials that we found are actually for the Raspberry Pi 4, so they'll work out of the box without any modifications on that platform. So the current way that the quadcopter interfaces with the motors is through a CrazyFly board that's mounted on top. So we're hoping that with our team, we would be able to mount the Raspberry Pi 02 on top instead and get it into the air. But unfortunately, we were unsuccessful about that fully. So before beginning work we would recommend that there should be some cross-compilation documentation on the wiki. So there should be a page called Compiling and Running Baremetal. We recommend you follow that tutorial to kind of get some understanding of how Baremetal applications are written, how they run, and how to load Baremetal applications using U-boot on the Raspberry Pi. So this is kind of a layout of the architecture of the FlyPi we proposed. So essentially, the Raspberry Pi has 4 cores. One of them will be running FreeRTOS with the modified CrazyFly firmware on it. The other 3 will have Ubuntu Linux, which will run the FlyPi adapter. So unfortunately, as shown in this diagram, no shared memory library exists for the Raspberry Pi 3 and 02. It only exists for the Raspberry Pi 4. So a shared memory buffer is going to have to be written by hand to communicate between those cores. And then a modified version of the CrazyFly adapter is going to sit on the Linux side. And instead of calling CFlib function, it's going to put packets into the shared memory buffer. And then on the FreeRTOS side, a modified version of the CrazyFly firmware can pick up those packets and then move the motors or do whatever needs to be done accordingly. So here's some next steps in the process. So the PiCroCart GUI was written as a standalone application by a member of the previous year's team from our team, Austin, and he wrote that using CFlib. It was all written in Python. So originally it didn't interact with the backend in any way, which was not ideal since we want all of the pieces to be talking. So although it works as its own standalone, we as a team decided that we would try to remove that CFlib part and then replace the C++ GUI with this PiCroCart GUI and have that send the packets back through the backend. And we did this. We started working on this because we felt that the PiCroCart GUI ran a lot faster than the C++ GUI. The code base was a lot easier to read. But however, this was a lot more difficult than we anticipated, and it's up to you guys to decide whether you want to continue working on it or not. Should be more videos and documentation on the wiki and on the YouTube channel. I will try to link some below in the description on where to go with that. So related to this is the revised packet structure. So one of the other members of our team, Steve, and we wrote a new packet structure that we think is going to help remove some of the slowdowns in the system and remove the need for those files for logging, or at least sending the path backwards, and instead send its own packet that has the logging or plotting data to plot on the GUI. We hope that this speeds things up. So I have the link here, as well as it'll be in the description of the video of the proposed packet structure that we made. This may require some modifications to the adapter and to the GUI to implement, possibly the backend as well, but should be pretty straightforward. So the plotting packet, as I mentioned before, eliminates the need for logging files. Definitely, if you're sticking with the C++ GUI, that's going to need to be updated to handle the plotting packet. And this hopefully also removes some slowdown in the GUI, since we theorize that some of the part of the slowdown in the logging is that it's competing with the adapter for locks on the files. So hopefully with the packet, we can remove that slowdown in the system. So now on to the FlyPi development. So here's one next step would be to write a more complex shared memory application. So the U-boot compiler folder in bmmemread has a Baremetal application that has an incredibly basic shared memory implementation. It's essentially a shared memory pipe. So there's one location with a flag. When the flag is set, then the Baremetal application knows to read. It reads, then it clears the flag, and then the Linux side can write to that again once the flag has been cleared. So this should be expanded to a ring buffer style system. There should be plenty of resources on kind of what that should look like from a theoretical perspective. And also just one more note that the current application only supports Linux as a writer and FreeRTOS as a reader, but this should also be expanded to go the other way, since we're going to need logging data to go back to the back end. Crazyflie firmware cross-compilation. So part of the FlyPi infrastructure is having the Crazyflie firmware, or a modified version of at least, running on the FreeRTOS core on the FlyPi. And so we began doing that. We started commenting out some of the hardware-specific stuff in the Crazyflie firmware. And so fortunately for us, the Crazyflie makefile contains native support for cross-compiling, just as with the Baremetal application, so you can follow somewhat of the same process. However, we did have some issues with trying to get the version of FreeRTOS that's used with the Raspberry Pi kind of integrated into the Crazyflie firmware. And it seemed to us, at least, that there was an issue between calling 32 and 64-bit versions of FreeRTOS. But that should have its own documentation, wiki pages, videos, to kind of go more into detail on that. So lastly, for the FlyPi hardware integration, our team didn't get to this as we had intended to. This was kind of the next step to get the FlyPi in the air. There needs to be some integration with the IMU. We didn't start on this. There should be plenty of details on the wiki, and Dr. Jones and last year's team, they have plenty of documents on hardware that should be much more useful in helping out than anything I can give. So here's some kind of task breakdown and prioritization. So I'd say first thing is obviously follow the bootcamp document, go through the lab, record any difficulties you have with the lab to kind of get an idea, a sense of where you want to go and how you're going to improve the lab. Next, I would say the plotting packet is a pretty high priority, since we think that it's going to speed things up a lot and make things a lot easier and shouldn't be that difficult to do. And would also be a very good starting point to kind of get acclimated with the infrastructure. Also, we would recommend starting early on Baremetal compilation, and following those tutorials, following those videos, kind of get an early jump on the FlyPi, because that's going to take a lot of your time, and the earlier you can get acclimated with that, the better. Also, at some point, probably in the fall semester, you want to look at the PyCore GUI, decide if it's worth your time. It may not be, and that's totally okay, but just dig into that documentation a little bit and look to see if you think that's going to be worth it for your team or not. Okay, starting in the spring semester or in the fall, if you finished everything from the first slide, You'll need to implement the shared memory buffer. That shouldn't be terribly difficult. It is going to take some time and some pretty thorough testing to make sure everything's working as intended. I'm sure there's going to be more can of worms to open with that we never got to, but it shouldn't be a super difficult task. So hardware integration is going to be a lot more difficult, but that is also going to be necessary for getting the FlyPi up in the air and connecting it to the CrazyFly firmware, which is also related to the next task, which once you finish cross-compiling the CrazyFly firmware, you can start adding the hardware stuff back in, but refactored to use the FlyPi motors instead. So that's everything that's recommended by our team. I'm sure you'll find more things down the road, but that's kind of our general summary of where we left off and kind of where we would have gone if we would have had more time. And so we wanted to just record this video to kind of give you guys a arrow pointing on where you should start going. Thank you.